Hello everyone. I welcome you to this class of econometric methods. Myself, Dr. Muhammad Imdadul Haq, an associate professor at the Department of Economics, Aligarh Muslim University. Today's lecture is basically an extension on the discussion on logistic regression. As we have seen in our previous class that in certain cases wherein the dependent variable itself is having a probability of 0 or 1, there is a probability of success or failure attached, or say it is categorical like male, female, good, bad, having a life insurance, not having a life insurance, having a house, not having a house. So if the categorical variable is like this, then we need to do a special type of regression which is called as, we can go into the realm of the linear probability models, but we have seen that in linear probability models there are certain issues. More prominently, the two issues are that in the linear probability model there was no mechanism to stop your values to be of probability to be more than or less than 1, this being one. And the second one was that uh, we assumed a linear relationship between uh, between the p and x, that is the independent variable, and the probability of it. Now, it's not necessarily true at most of the times. We need to accommodate for nonlinear relationships. We have seen the reasons in our previous class. Also, there were issues with heteroscedasticity and normality over there. So, the way out of that was a logistic regression. We have seen what is the probability over there and how come we manage both the things, that is our probability don't go more than 0, less than 0 and more than 1, and also there is an non-linear relationships. But the estimation of this logistic model, and also we have discussed in brief the probit model. So we will just take at the moment the logistic model. It is basically solved through softwares, and today in our class we will give you a view of like how do you have studied the theoretical items which were there in logistic regression. Now we will see that we will take an output from SPSS. It's a common statistical package used in business and economics and management, and it is a good one for primary using on work on primary data and all. So the output sheet will be there, and we will just see how to take out how to accommodate, how to interpret the results of this binary logistic regression. So we will see how the interpretation is to be done. Take a case wherein suppose you are doing some primary survey and you have the data of the people having a bank. So your dependent variable, whether you have an account or you don't have an account, that is what is your dependent variable. And independent variable could be things like age, gender, income, education, awareness, and things like these. They can be categorical, they can be on ratio scale. That's a completely different thing. Now, there are many things. So when you do it through SPSS, there are a few things which are reported. Um, Particularly, the first section of the result is on where the software just estimates the model, assuming only the intercept and ignoring all the explanatory variables. And then basically it does a comparison between this model and the second model, wherein it has incorporated the impact of the explanatory variables. So we have ignored many of the tables. Now we are taking the main tables. Now the first one is this omnibus test for model coefficient. This omnibus test for model coefficient in logistic regression is a statistical test that evaluates the overall significance of the predictor variables in the model. It assesses whether the set of predictor variables taken together significantly contributes to explaining the variation of the outcome variable or not. Now here there is that overall model fit is there, that is the test evaluates whether the logistic regression including all the predictor variable plays a better fit to the data than the null model which I was referring, that includes only the intercept term. In other words, it tests the hypothesis that at least one of the predictor variables in the model has a non-zero coefficient. Here we do the significance testing. Again, normally we do it at 0.05 level, and so this sig dot value, this is nothing but the probability value. So when we are normally checking at, when we are checking at 5%, this means 5 divided by 100, this is equal to 0.05. So 0.05 is the cutoff. If my p value, that is the significant value which is visible over here, is more than this, then the case is not significant. If it is less than this, then it is significant. So that's what we are seeing over here. The chi-square test is being given, and we see that it is significant, significant, significant. So the p-value associated with the omnibus test is less than the predetermined significance level, commonly assume take it as 0.05. It suggests that the set of predictor variables as a whole significantly predict the outcome variable. Now we move to the next case. Here three statistics are reported: log likelihood, Cox-Snell and Nagelkerke. So these are basically the variants of R square. This log likelihood measures how well this logistic regression model predicts the observed outcome based on the predictor variables included in the model. A smaller log likelihood ratio indicates a better fit, meaning that the model is better at explaining the observed data. Then the next one, Cox-Snell R square, is one of the pseudo R square measures commonly used in logistic regression. It is a measure of the proportion of the variability in the outcome variable that is explained by the predictive variables in the model. But unlike the traditional linear regression where R square represents the proportion of variance explained, in logistic regression the concept is adapted due to the non-linear nature. Then we have this Cox-Snell R square is calculated using this maximum likelihood estimation. We have earlier also discussed, we measure this, or we estimate this logistic regression model by maximum likelihood of the where the null model with no predictors and the maximum likelihood of the model with predictors. So this also the value ranges from 0 to 1, and a higher Cox-Snell R square indicates that a larger portion of the variability in the outcome is explained by the predictors in model. However, the case is the same, what you say, it tends to, it represents the proportion of variability. It ranges from 0 to 1, but it represents the portion of variability in the outcome variable that is explained by the predictor variable in the model. But unlike this linear regression, this R square of Cox-Snell, it cannot reach 1 even with a perfect fit of the model due to the logistic nature of the regression. Then the last one, Nagelkerke R square, it tends to provide a higher estimate to the proportion of variance as compared to this Cox-Snell. In this Nagelkerke R square is a useful, again you say, and pseudo R square measure in logistic regression, providing an estimate of the amount of variation in the outcome variable explained by the predictor variables. However, it is important to remember that like other pseudo R square measures, it has limitations and may not fully capture the complexity of the model or the relationship between variables. Therefore, while using these R square methods, these pseudo R squares as they are called, which should be used caution, and they should be used together in order to give a better predictive accuracy. Now, as we see over here, this log likelihood as lower values indicate better fit. meaning the model's prediction are closer to the observed outcomes. But in this case, it is quite high, so it's not a very good fit. Also, Cox and Nell, unlike traditional R square regression, it doesn't have the same interpretation as the proportion of variance explained. In this case, the value is only 0.132, indicating only or above on an average 13.2 of the variance in the dependent variable is being explained by its relationship with the independent variable. Again, this Nagelkerke R square, it is here 0.198. It suggests that the independent variable in the model explain approximately 19.8% of the variance of the dependent variable. So this log likelihood, Cox and Nell and Nagelkerke, these are the pseudo R square measures that are reported by the software. Next, there is another classification table is given in SPSS. It provides a summary basically of the model's predictive performance based on the observed and predicted outcomes. It has the data for observed versus predicted categories. This table compares the actual outcome with the predicted outcome generated by the logistic regression model. Then there are the frequency counts that is present over there. It shows the number of cases falling in each category of the observed and predicted outcomes. And also we have a percentage distribution, that is, in addition to the counts, SPSS provides the percentage distribution of each cases in the category. We can see over here what variable 7 is the dependent variable, and apart from that there are 6 other independent variables. So in the cell where this observed 0 is 0 and predicted is 0, is the correct percentage is 94.1%. I'm referring to this 94.1%. This means that 94.1% of the observations where the actual was 0 were correctly classified as 0 by the model. So, and in the next one, in the cell where observed is 1 and predicted is 0, the percentage correct is 24.7. So this means that only 24.7% of the observations where the actual income was 1 were correctly classified as 0 by the model. So it's a fairly good fit in that case. Now this represents this overall percentage. It represents the overall accuracy of the percentage of correct classifications made by the model across all the observations. In this case, the overall percentage is 77.3% of the observations. And also here there is a cut value is mentioned in the software. It's not visible, but it will be there in the output. This cut value is normally mentioned as 0.5. That is, it is the classification threshold used by the model to assign observations to one of the two categories. Observations with predicted probabilities greater than or equal to 0.5 are classified as 1, and those with predicted probabilities less than 5 are classified as 0. So this is what the classification table tells us all about. Now, this is the main assets. The table here we had B, SE, Wald, and degrees of freedom is okay, and then the significant and XB, exponential of beta. Now the coefficient column beta represents the change in the log odds of the outcome variable for a 1 unit change in the corresponding predictor variable, holding other things constant. The exponential of these coefficient exponential b gives the odds ratio associated with each predictor variable, which indicates how the odds of the outcome change for a 1 unit change in the predictor variable, holding all other things constant. Then standard error is, as such, we know has the common meaning. Then here there is a new thing, that is Wald test. The Wald test over here assesses each coefficient, that is a beta. Each beta is significantly different from 0 or not. In logistic regression, each coefficient represents the effect of one predictor variable on the log odds of the outcome variable. Therefore, Determining whether a coefficient is significantly different from 0 helps identify which predictor variable are statistically significant in predicting the outcome. In logistic regression, the significance of the wall test is typically assessed using the p-value. Again, the column for sig is nothing but what it gives the p-values, and again we apply the same logic. If the p-value is if the significant column values are less than 0.05, it means they are significant, and if it is more, then we say that it is not significant. Then the last column is your exponential b, and that is your odds ratio. We had a discussion on odds ratio in our class of logistic regression. It is what p divided by 1 minus p, and this is what is instead of in logistic regression model, instead of this beta, more importantly this odds ratio is reported and is also explained. Now let us take one example. Let us take one of the, we explain one of the rows. Now what is over here is, that is the variable 1 is the first independent variable included in this model, and the b value is 0.156. This means that for a 1 unit increase in variable 1, the log odds of the dependent variable, that is your outcome of interest, increases by 0.156. Since this is the logistic regression, it is about the change in log odds and not the probability directly. So this can be, it is not exactly directly it is not exactly the probability, it is the log odds. It is the log of odds. Now the standard error associated with this variable, okay, where did it go? We are going to explain this now. So we have our standard error. So the standard error associated, the standard error associated with the coefficient of variable is 0.065. It indicates that there is certain amount of uncertainty or variability in the estimate of the coefficient, but nevertheless a smaller standard error suggests that it is more precise. Now evolved statistics associated with this variable 1 is 5.782. This statistics help determine the significance of the coefficient, and higher values of the Wald statistic indicate a higher coefficient, and then you have the significant column. Now here the value is 0.016, so this is 0.05 and it is 0.016, it is lower, so this variable is significant, and then this variable is significant over there. And the last one, the last thing which we have over is the log of odds, and the value of that is 1.165. SPSS refers to it as exponential b. This value represents the odd ratio associated with a 1 unit increase in variable 1. In logistic regression, this exponentiating the coefficient gives us the odds ratio, which quantifies the change in odds of the dependent variable for each 1 unit increase in the independent variable. In this case, 1 unit increase in variable 1 is associated with 1.169 times increase in the odds of the dependent variable. So this was an explanation, and we can continue with that same explanation for all other variables. And if you see, this is also this is significant, this is significant, this is also significant. This variable is not significant, and again this last variable is significant. The intercept term is also significant. So for variable 5, for variable, and also you can see that the b, it becomes negative. For all others, whether it is more than 1 or less than 1, that's a different story. But this one is negative. So the Waltz statistics do not indicate that it is significant. It is not significant. The significance value confirms this, and that the variable 0.05 is not significantly associated with the outcome variable, and the odds ratio further suggests that this variable 5 does not have a meaningful impact on the odds of the dependent variable. So except for this variable 5, all other variables are significantly related with the dependent variable. I hope this discussion on interpreting the output of logistic regression is clear with you. With this, I end this lecture. Thank you. Goodbye.